Well, hello, welcome back. Today we are learning about function notation. And so in section 3, which was yesterday and what you practiced today in class, you learned that you can write a linear function in the form of slope-intercept form y equals mx plus b by naming a linear function f. You can also write the function using what we call function notation. So notice, compare these two, y equals mx plus b, f of x equals mx plus b. One thing has changed, the way we've labeled the output. That's all that has changed. This enables mathematicians, scientists, statisticians, anybody that works with functions, the ability to work with more than one function at a time. So think about if we have y equals mx plus b and you have y, you have all these functions called y, you wouldn't know which one you were talking about. We have the ability with function notation, right? It's just another name for y. If f is a function and x is its domain, f of x represents the output or the range of f corresponding to the input. So we can use any letter other than f to name the function, such as g, h, anything. So if you're working with two or more functions, you name them two different things. We can use this then to compare functions and so forth. So let's do that. Another key idea is that if we have the graph of f of x plus k, and it's a vertical translation of the original f of x, okay? And we're talking about where k is not equal to 0. So because here, the black line, f of x, that k is equal to 0. That's a proportional relationship right there, straight line through the origin. Notice that when k is greater than 1, the translation will go up, right? It'll just be y-intercept of a positive number. In the red, f of x plus k, when k is less than 0, I don't know if I said 1 or not, I don't know. Anyway, greater than 0, less than 0. The red graph shows us all of the functions that would translate down or would have a negative y-intercept. So in vertical translations of linear functions, the graphs have the same slope, but different y-intercepts. So it's really not a big deal. We're just going to be talking about them, kind of getting to start to practice to compare to a parent function. When we talk about a parent function, we would talk about this f of x, right? The black line here would be the parent function. And then if we graphed another one, called it g of x or whatever, and said, how do they compare? Well, this would be a vertical translation however many units up. This red one would be a vertical translation however many units down. So we're going to get a little bit of practice doing that. In the example from your book, we'll practice evaluating. So x is equal to 2. All we do, so this is x, we substitute in the 2. So f of 2 is equal to negative 1. Okay, when x is equal to 2, f of x, or the output, equals negative 1. Sometimes we also say f of 2. We can write it like this. Well, isn't that fun? How? F of 2 equals negative 1. Okay, maybe a little bit. I like that. A little bit better. Okay, crazy. Don't know how that changed. All right, and moving on. So on our own, we want to evaluate. So let's do that. It's the same as if you made an input-output table. In this case, we'll put the output as f of x instead of y because that's literally what the output is. The inputs then are negative 4, 0, and 3. So what does that look like? It looks like right here. It looks like, 2 times negative 4 minus 5, right? And that's going to be negative 13. 2 times 0 minus 5, negative 5. And 2 times 3 minus 5, or 6 minus 5, which is 1. We could also say that f, that's supposed to be a lowercase f of negative 4 is equal to negative 13. And notice that from this notation, you see the ordered pair, negative 4, negative 13, x, y, okay? F of 0, right? If the input is 0, we have -5. And finally, f of 3 is equal to 1. Okay, we could do the same over here for g of x. We have our input, and we have our g of x, or our output. Same input values, -4, 0, and 3. So we would have negative, or the opposite, so it's taken the opposite of x, so it's the opposite of -4, right, -1, which would be a 3. And then we have the opposite of 0, does not even matter what that is, which would be -1. And then the opposite of 3 minus 1, which is -4. So again, g of -4 equals 3. G of 0 equals -1. And g of 3 equals -4. And again, in this notation, we see the ordered pair, 3, -4. Okay? Looking at 3, it's asking if f of x is equal to 6x plus 9, what would x be, right, if we had an output of 21? So if f of x is equal to 21, it says find the value of x, so that the function has the given value. The given value is 21. If we want the output to be 21, we simply state 21 is equal to 6x plus 9. So we'll subtract 9 on both sides. Maybe I should move this a little bit. Okay. And then we'll get 12 is equal to 6x, so that x is equal to 2. Okay, f of 2 is equal to 21. I guess we need to see what this is. G of x is -1, so the output is -1. So we simply put -1 here, and we solve for x. That's all we're doing. Inverse operations, subtracting 3 from both sides. We get -4 is equal to a -1/2 of x, so we multiply both sides by -2/1 times -2/1, and we get x is equal to 8. Okay, make sure that you have that written down before I clear, because we're going to get ready to do some graphs. This is a little bit of a longer lesson. Let's go ahead and do some graphs. So here we go. We're going to graph the equation just like we graph a slope-intercept form, because this is the y-intercept and this is the slope. So we have a y-intercept of -2 and a slope of 3. So 1, 2, 3 over 1. And again, you use a ruler. I, however, have to kind of just do a couple. Okay. Ooh, draw a straight line. And moving on to this one, we will graph the y-intercept at +4, and we have a -1 slope. Look how nice and neat that's going to be. And we graph, the line with a straight edge. You use a straight edge. Okay, here we have a -1. I'm going to go ahead and do 1, 2, 3, and then back 4, okay, because I'm going to be going right into behind my little picture there. Okay, that's probably how I turned it blue that one time. Okay, but we've done this many a time. So using the slope and intercept form works just the same. Okay? All right, now what we're going to do next is compare. We're going to compare. So let's start by graphing f of x is -2. So remember, we have this. So we have down 2 and over 1, down 2 and over 1, or up 2 and back 1, and up 2 and back 1. Okay, so this is the graph, of f of x. Now, if I change colors here and I do red, I would graph g of x. Okay, let me just label this. This is f of x. Okay, and then I'll do g of x. So g of x is a +3. 1, 2, 3. God, that's a bad that is. Okay, down 2 and over 1, down 2 and over 1, that you'll hardly be able to tell that these two are parallel. Yikes, because I'm not using a straight edge. That's how important they are. So this is the graph of g of x. And then when we compare them, we would say that like g is, the graph of g is a translation. So the graph of g is a translation. And here's that k value, right? 3 units up of the graph of f. That's it. That's all we have to do. All right. So again, we have the parent function, so to speak, which is down with a slope of -2. So same parent function here. All right. And this is f of x. And then we have h of x. So 1, 2, 3, 4, 5. And we have the same slope. So in this case, we want to say that h, okay, so the graph of h is a translation 5 units down from the graph of f of x. Okay, so from here it went down 5 units, and we see that with this k value, right? That's how it translated that many units down. So we're just putting two graphs on there and then comparing them. Okay. Vocabulary and concept check. Identify which problem you are answering or question you are answering. Remember, this is a way for us to get you to write about mathematics. Knowledge will bring you the opportunity to make a difference. All right, and I will see you in class. Be sure to let me know if you have any questions. Bye for now.